Hello, I am Alexandra Sandulescu, and today I am talking about memory corruption attacks in the Spectre era. In this presentation, I cover a special kind of memory corruption attacks, namely speculative control flow hijacks. Respectively, I'll discuss the motivation behind this research, how these attacks evolved from combining memory corruption attacks with Spectre, what is needed to carry out such attacks in real-world scenarios, and lastly, I'll show how to mitigate them and at what cost. This research is motivated by two main things. First, exploiting memory corruption vulnerabilities is hard. The attacker must have the means to bypass strong hardening measures like stack smashing protection used to hinder stack buffer overflow, control flow integrity used against indirect cold target corruption, and the mechanisms used by memory-safe languages. To overcome these, usually a combination of vulnerabilities is needed, which might not always come easy. Second, Spectre is a very powerful vulnerability to have in hand to use in combination with other vulnerabilities. By combining unexploitable memory corruption vulnerabilities with Spectre, we may obtain a new exploitable vulnerability, an extended attack surface, and eventually arbitrary memory read. We make the observation that memory corruption vulnerabilities and speculative memory corruption are quite similar. Here we see why. On the left, the attacker controlling the array index and value can write attacker-controlled data past the array size because the inbounds check is missing. On the right, even if the inbounds check is present, the CPU might speculate on the condition. If it mispredicts, the memory corruption will still be executed, but speculatively. In both situations, the memory corruption code is executed, though in the speculative case, the instructions get discarded. Can speculative memory corruption still lead to arbitrary memory read? To get the answer, we first discuss Spectre. The Spectre class of attacks is broad, and by now, some of its variants have been mitigated at OS level. We focus on Spectre variant 1, or speculative bounce check bypass, because it is powerful and existing mitigations are not enabled by default. A Spectre v1 snippet consists of a bounce check followed by access of secret data. The secret data access itself is not dangerous, but the threat lies in the subsequent instructions which use the secret values and eventually leave microarchitectural traces. As we can see in this snippet, when misspeculation occurs, the if statement body gets executed speculatively, therefore leading to cache traces being accessible to adversaries. If an adversary triggers this behavior inside the victim, they achieve arbitrary memory read of victim's memory. In practice, this code snippet is scarce and secret data is protected by different means. Nevertheless, a speculative memory corruption attack can be carried out if the adversary can trick the CPU into executing its own instructions speculatively through speculative control flow hijacking. Speculative control flow hijacking can be conducted in two ways. One way is through speculative overwrite of the edge. On the left, we have the forward edge example in direct color jump. When the CPU mispredicts on the condition, the address is speculatively overwritten with the attacker desired value. This value can point to attacker control code or sequence of rob gadgets. Subsequently, the CPU speculatively executes the call instruction, directing the control flow to the attacker address. On the right, the same situation exists when a return address stored on stack is overwritten with an attacker's target. In these examples, the full attack is conducted speculatively. Next, we discuss how a traditionally unexploitable memory corruption vulnerability can be used in combination with Spectre to achieve arbitrary memory read. In this case, the edge overwrite is performed architecturally. The architectural edge overwrite allows the attacker to use the full speculation window for arbitrary memory read, increasing its chances of succeeding. The attack, which leverages architectural edge overwrite, is comprised of three phases. First, The memory corruption vulnerability overrides the edge with the attacker desired target. The mitigations in place would normally abort execution and leave the attacker with no means of conducting the attack. However, the execution abort might be delayed if the CPU mispredicts on the mitigation integrity checks. This delay leads to speculative execution of the wrong program path with all attacker payload in place. This method provides the attacker enough transient instructions for obtaining arbitrary memory read. We tested both types of attacks on different memory safety mechanisms to understand where defensive software security stands in front of Spectre. One security defense mechanism we analyzed in detail is stack smashing protection, or SSP. The SSP mechanism blocks the exploitation of a potential buffer overflow vulnerability by aborting the execution before the attacker redirects the victim control flow to its desired location. This code snippet shows a function, f, which suffers from stack buffer overflow but is protected by SSP. In the paper, we present an end-to-end attack against a vulnerable version of libpng, also protected by SSP. We follow the execution of this snippet. First, the canary is pushed on the stack and the buffer is allocated. By copying attacker data in the buffer without proper size checks, the stack contents is controlled by the attacker. Normally, the canary check instruction aborts the execution. But in this case, the CPU mispredicts the canary check and therefore starts executing the wrong program path speculatively. At function return, the control flow is redirected towards the ROP gadgets. The whole purpose of the speculative control flow hijack is to direct the victim process to attacker-controlled code speculatively. The attacker-controlled code is represented by a ROP sequence which leaves microarchitectural traces inside the cache so that these traces are read by the attacker process later on. Here we see what are the speculative ROP effects on the cache state. On the right-hand side, we have multiple cache zones or a cache array. The cache array size is 256, one for each possible byte value. The cache array is a shared memory region between attacker and victim, in this case a shared library area. Prior to the attacker flushes all contents of the cache array. A green box means that the memory associated with that location is uncached. On the left is the ROP gadget sequence, which acts as side channel send. The first instruction loads a victim secret byte from an arbitrary address chosen by the attacker. The second gadget multiplies the byte value with the size of each cache location on the right. Next, the cache array base address is added, which results in R0 containing the address of one of the cache locations in the cache array. The last gadget performs a load from this address, changing cache state. Now, only one of the locations in the cache array is cached, therefore revealing the victim byte value. Here we see on a higher level how the side channel is used to transfer victim secrets to the attacker process. After speculative control flow hijacking, followed by side channel send via ROP sequence, the victim secret is encoded in the side channel. The attacker then reads the encoded secret in the side channel receive phase, therefore obtaining the secret key. The leak rate recorded in the SSP attack is 0.3 bytes per second. Together with SSP, we inspected other memory safety features like different CFI implementations and 2 memory safe languages. The results show that all, apart from LLVM CFI, are vulnerable to speculative control flow hijacks. Moreover, in all vulnerable cases, the mitigation itself provides the speculation-inducive instruction that the attacker can leverage to trigger speculative execution of the wrong program path. For all the memory safety mechanisms shown here, we developed proof-of-concept attacks. The speculative control flow hijacking attacks are not blocked by existing Spectre mitigations unless they address specifically Spectre v1. The attacks rely on the control flow being transferred to an attacker target during speculative execution. The control flow metadata involved includes call and jump targets, the return address, or array indices. One approach to mitigate these attacks is to stop speculative execution before control flow transfer instructions like call and jump via LFENCE. The maximum performance overhead we measured on Spec CPU 2006 benchmark is 100%. The high performance penalty comes from blocking speculative execution entirely. An alternative would be to ensure that control flow cannot be transferred to attacker-controlled locations during speculative execution. In this case, all control flow metadata are masked before control flow transfer. The implementation of the masking-based mitigation is done via selective speculative load hardening. As expected, the overhead recorded is lower than the LFENCE one, reaching a maximum of 13%. As a result of our work, the Go community added support for the masking mitigation in the latest release. We conclude with the following observation. First, current mitigations implementations are not only partially protecting software, but may be leveraged to trigger Spectre. Moreover, using Spectre, we transformed currently harmless vulnerabilities into arbitrary memory read by leveraging the mitigation checks as speculative inducive operations. Lastly, the masking-based mitigation shows hope in hindering speculative control flow hijacking attacks. To find out more details about speculative control flow hijacking attacks, you can read our paper, which is available on arXiv.